What we're going to be going over here is the directional derivative here of a production function, and our production function is going to be similar to the Cobb-Douglas production function. Okay, so this is going to be our production function here. We're going to have some Q, that's going to be our output here, and it's going to really be some targeted profit here that we have. And then that's based on our function here. We're going to have a revenue per unit, or what we sales price per unit here for our product at $1,400, and we take that times some material and labor inputs here. We only got two different inputs, and for material they're raised to an exponent amount here, 0.5035, which really represents about 50.3% of the revenue based on whatever material input we have. And then we take that times some labor input here. So our labor input is 0.3215, which represents 32.1% of the revenue based on what labor we put in. But we're also going to include in this production function here where we're going to have to abstract out the cost here. So on a per unit basis here, we're going to have $350 per unit here of material that goes into our product, and then $200 per unit here of labor that goes into our product. So this is our cost here, and it's being of $350 in material per unit and $200 in labor, and that's being subtracted here from our revenue per unit here, $1,400 times our exponential amounts here for material and labor, and that equals our profit here. Okay, so what we're going to be doing here, and let's go down and look at it. We're going to be working with we're going to be looking at what they call again the directional derivative here. We want to figure out we're going to be looking at two different points here, two different targeted points here, and look at the change in our output here, our maximum output, or how we affect our output based on what we're going to be looking at here. So what we have here, I'm just showing it here, we have this gradient path. Well, first off, I want to just say I've done a linear program on this production function here, and our optimum maximum amount here based on, I had some constraints in here as well. Based on those constraints here, I have 67 units of material, 75 units of labor, and that equals $8,150 here in profit. So I know that that's my optimal point here, and based on that point here, I'm going to establish that as my target point here to set up my gradient path. And the gradient path is really the greatest increase here in our output at some targeted point. So that's what I established my gradient path at. But I not only have this point here sitting at 67 and 75, also I'm going to have another point here where I'm looking at 5 units and 6 units here of material and labor respectively. Okay, so let's just go and break this down a little bit here. So what I have here with this production function here is shown in blue. I've got it graphed out. So I've got, based just looking at our point up here, I have 70 labor I'm showing along this axis and material along this axis, and then our output here, our profit, I'm showing on the vertical axis. So just looking at these yellow lines that curve up here, those are our change in slope, or the tangent path for, in this case, the material input and the labor input. You can see just how they curve around here. So it gives you an idea of what's going on here. And then I've got another cutting plane going through here, an iso curve. So let's just move over to our, and then these little red lines here, those are iso lines, or equal product lines shown here on our production function. I've got it graphed out. Okay, so let's move over here and let's look at really a gradient vector, or gradient vectors here that's involved in this equation here, or this production function. Really, that's the change in slope. So what we're showing here along my lower axis here, horizontal, I got the the material input, increasing in this direction, and along the vertical axis, I'm showing an increase here in the labor. And really, we've got those two different points that we're going to be looking at. This first point here, which is very low here, based on our gradient path here, and then we got this other point here. This is the one that I come up with the optimal profit, or optimal mix here of material and labor to come up with our profit. And then we have some constraints. I'm not going to go into all those. This green area is really the feasible area. But when we're talking about gradient vectors, really, we'll look at it in a different look at a different plot here. We got the arrows a little easier to look at. But what we have here, when you're talking about the gradient plot, you've got these arrows. It's good to lay it out here based on some plotting software. And the arrows point in the direction of the greatest increase here that you're looking at. So in this case, we've got arrows pointing this way, arrows pointing in this way, an arrow pointing to some point here. Okay, so let's do just a little analysis here. So we know we've got some constraints here based on our material and labor inputs. The green area is our feasible area. And looking at this first point here, that is our, we're going to have a target point. Maybe let's go down and look at it. That's this target point here. Moving back to our production function here, we're going to have 6 units of labor, 5 units of material shown here. And that we had a profit. I put that in. We come up with $2,650 our profit. But all I'm just showing is those tangent lines coming in here based on the labor and material inputs here. And then this is our gradient path here again. And really, these yellow lines here, they're really the change in slope or the tangent path that our labor and material inputs follow here. But nonetheless, you can see the input here. It's showing it here where you just start out here. That's those 5 and 6 units. So moving up to our gradient point, that's shown here. But the key is with this gradient plot here, this is what we're looking at. You see this blue line moving up in this direction? That's at 5 units of material, 6 units of labor. That is what the direction here of the greatest increase, or moving up here, that's the gradient path of the greatest increase at our based on our targeted point here. And a targeted point in this case is 5 units and 6 units respectively. But you can see it going up in this direction. And then the other thing is we've got this is an ISO curve, the blue one here, and that refers to those 5 and 6 units here. That is the ISO curve, the equal product curve here. And you can see the gradient path is moving along that blue line in this direction. And then you've got this other point here. This is our max output point here. We come up against our constraints. It's also up against our equation as well, our production function. But the point is here, when we moved up to this point here, our gradient path is changed. It's following this red line here, and it's actually sloping down. And we're at a zero increase here is what we're going to be going and looking at, a zero increase here in our output here. This is our maximum output based on the production function we have. But nonetheless, it's moving in a different direction here. So this is what we're going to be looking at. We're going to be calculating our directional vector here based on this first point where we have this increasing amount here. And then we're going to have the directional vector here looking at the case here where we're going down here. Okay, so right, let's go on. Maybe let's go and let's look at the other ISO curve here, and then we'll move on. Okay, so this is my other ISO curve here. I guess I could have put it in here initially here, but this is the case here where we got those same outputs that we're looking at, the ISO curve here at 5 and 6 units, and the directional gradient vector here. But the key is here, and then we got these other ones here. The key is these arrows here. When you do these gradient plots here, in this case I use some big arrows here. The software is telling me that pointing in these directions here, the bigger the area, this is where we're going to have our greatest increases here in input for labor here and material over here. But as we increase move up our gradient here, and maybe let's go over and make up the comparison over here. So if we go to our 3D plot here and we start moving up in this area here, we start at lower inputs and we move up here, this is where we're going to get lesser and lesser increases in our output or our profit in that case is here. We got, when you're sitting here in those lower levels here, this is where you're going to have the greatest increases in your profit based on material and labor inputs here. But nonetheless, gradient plot here, big arrows mean you have a greater increases, and then look at the direction they're moving in, pointing in this direction here for material and labor. They're all pointing in some direction here. And actually, the ISO curve here for this point here, there really isn't an ISO curve. It's just, you're going to see it's just a point here. So we don't have an ISO curve. For our lower one, we do have those ISO curves here. And we also have that gradient vector going up this way here, gradient plot. But for when you get to this maximum one here, you're going to see it topped out and it's not. It's going to actually be going down in a negative direction or at a 0 direction. Okay, so we got our gradient plot. So let's just go back over here. Now let's look at, this is for what we're going to really be calculating, this directional derivative here. And that's really, and we're looking at this first point here, 5 and 6. I'm just laying it out here. This is our initial point that I'm looking at here, 5 and 6 units here, material and labor. What we're going to have here is the directional vector is really composed of these yellow vectors here, and those are really based on gradient and directional vectors here, these yellow ones for material and labor here. Based on those inputs here and their vector inputs, gradient and directional amounts, you're going to get a directional derivative here, this red one showing up here, and it's got a plot here. It's sitting on some plane here. I got it shown sort of in green here. But this is going to be the unit output or the slope here that we're talking about at that particular input or target point here for material and labor. Okay, so that's our first point that we're going to be looking at. And then let's move over here. This is going to be our second point. This is that point here, 67 units and 75 units, the optimal amount here for material and labor. And just looking at that here, if we move up to our gradient vector, you can see it's this one sitting right here, sitting at our up against our constraints here. And actually, if you pull the constraints out and just did an optimization based on the function itself, this would be the maximum amount here. That's why we don't have any ISO curves at this point here. All right, it's just a point. So moving down here again, these are going to be our gradient and unit vectors shown here in yellow. And then the directional derivative here, or let's look at that. The directional derivative is going to be this red one here. And that's really the change in unit output or the slope here at that point. So that's really the change in our profit here based on our material and labor inputs. Okay, and then again, these gradient vectors, these yellow vectors here for material and labor, you take the gradient, and this is what we're going to be working with. The gradient vector times the directional vector is equal our directional derivative here. And then I'm just showing these yellow slicing through our production function here. That's just an ISO curve, and they could put it in at any value. I just put it in here at a profit of $2,650 here. I didn't put one in up here because the ISO curve would be covering up all our directional derivatives, and all our function would be topping out right there, because that's where we're sitting based on that production function. Okay, so now we'll go in and we're going to calculate our gradient vector and our unit vector, or directional vector, and then we're going to come up with our directional derivative. Now we have to calculate our gradient based on our vector path here. Now remember, this gradient, that's the direction of the greatest increase here. And how we determine that gradient, we just take the partial derivative of our function here, and we do it with respect to material and with respect to labor. Okay, so just looking at our production function here, what we have to calculate is these yellow vectors here, at least the gradient amount in this case here. Really, that's the change in slope, or the rate of change here for labor and material here. And they're following along this gradient path here that we have, our targeted point here. And we're going to be looking at two different points here, that first point here and then our second point. Okay, so let's go down and let's make our calculations. Okay, so first of all, this is our production function here I'm showing here. Now, what you want to do is you want to use some software package here to determine your partial derivatives. So what I've done here, I've just taken a partial derivative here with respect to material here, production function, or our function here, and also with respect to labor. So then with those partial derivatives here, we can determine our rate of change, and that's really the slope here. So just plug in this case, I have that as 5 units of material, 6 of labor. I plugged them into our partial here for our material and labor. So for our material here, change in slope is 213.98. That would be like dollars here. And then for labor, it's 100 here, 0.1. So the gradient vector here is what we have to calculate. So we just take our slope here for our material, shown as x, the x direction here. That's 213.98 here for our vector here in the x direction, our material, and then add to it for the change here in our labor at 100 here. So put that in. So that's our gradient vector. That's the direction of the greatest increase. And based with this gradient vector, we'll be able to calculate our directional derivative. And then if I went over here and did the same here for this other point, 67 and 75, and if I plugged my numbers in here for my partials for your material and labor, I would have come up with my, for material at a slope of 0.19 here. Essentially, we're at a zero slope here. And for labor, negative 0.24 here. So we're at a zero slope here. So our gradient here is essentially zero here, 0.9 times in our x direction, and for material, negative, slightly negative here in our y direction here for labor. So we're at our maximum output, and that's really why I wanted to look at both of these cases here. Okay, so if we've gone back up to our diagram here, so now we figured out, we got our gradient vector here to change in slope for our input here for 5 and 6 here in material and labor. I got a rate of change here, 100 in labor, 213 here in material. Okay, so this is what we calculated, the gradient here, or the rate of change here at this specific point here, 5 and 6 units of material and labor, and we've calculated both for material and labor the gradient value of these yellow vectors. And then if we moved over here, moved up to our other point here, 67, 75, we've done the same thing. Got labor here, material here. And this is where the change in slope's approximately zero. We're sitting at zero here. And these green arrow plots, or these green meshes here, that's really a vector plane. We just plotted a vector plane here based on the gradient at that particular point. Okay, so if we move over here, just understand what's going on here, this gradient path, this is this red one here, based on our targeted point here. And remember that targeted point I set at, I maximized that function here based using a linear programming here to determine those different inputs based on that function, our production function here. So the gradient path here is really moving from 0 up and on here. That's really a proportional increase in material and labor here. This is gradient path is following our maximum output here based on our linear programming. And then just to what you're showing here, these again, these red lines here, these red curved lines, those are the level curves, or what they call the iso or equal product curves. And just remember, when you're looking at those here, the gradient vector is really perpendicular to those level curves. When you're dealing with a level curve and you're plotting them out here, the gradient vector is actually perpendicular to it. So if you're looking at any level curve, just get the idea here. Your gradient, your greatest increase here is perpendicular to the level curve. And then the other thing was our tangent paths, those yellow paths I'm showing, and this is for that targeted point here, 67, 75. These yellow lines here are really the tangent path, or the change in slope for material here and labor here. And really, you could look at them in terms of marginal product here, and that's really looking at the derivative here, in partial derivative for material and labor, the marginal, what they would refer to as the marginal product. And then one other thing, moving down here, this targeted gradient path, again, I'm just showing it here. And this is where I've got them laid out here for that first point, that 5 and 6 point, and then 67 and 75. So the idea is here, the tangent path or the change in slope. I'm just overlaying each of those so you can see the difference between both of those different inputs here. 5 and 6, material and labor, and 67 and 75, material and labor, just to get an idea what's going on here. Okay, so now we can go and we can make our calculation here for this directional derivative. Now we can calculate our directional derivative or vector here at the points that we're looking at, and that's really the slope of a tangent plane in the direction of the point. And it's really the rate of change in that specified direction. So we have these two different points, 67 and 75 here for material and labor units. And then we also have that 5 and 6 points here for material and labor. And we're really starting at a point here, 1 unit of each here for material and labor. And we're going to be looking at our directional derivative based on these numbers here. Okay, so for our plot here, our gradient vectors, we already calculated those. Those are our yellow vectors here for material and labor here. But what we have to calculate here is this directional derivative or directional vector here. And that's really the slope here of looking at our a tangent plane, or the slope here, based on our targeted points here. So this is what we're going to be calculated. So we got this tangent plane, or it's the change in slope here for both of these two different points that we're looking at. Okay, so let's go down here. So again, the direction of the greatest increase is really the vector dot product here between our gradient and our unit vector. So we've calculated our gradient vector here, and we'll start with our point here, 5 and 6 inputs here for material and labor, and then we've got that calculated. We've done. Now we have to come up with the directional unit vector based on our gradient here. So let's go and let's see how we do that. So our directional vector here for points 5 and 6 for material and labor is shown here. So what do you do here? All you're having to do is just take a right triangle, material and labor here, and you're trying to figure out the hypotenuse here in a unit amount. So looking at our material here, 5 units of material, and then you divide that by squaring 5 plus squaring 6 here, and then just take the square root of that here and divide that into 5 units here of material, and you're going to get 0.6401 here. So that's how you have to transform whatever directional vector you have to transform it into a unit vector here. And actually, I've done this with the computer program has done this with MapleSoft here. And the same thing for 6 here. Just go through the same routine and figure out your 5 squared plus 6 squared, square root of that, divide that into a unit of 6 here for your labor. And you're going to get a unit amount here, 0.7682 here. So that is the key point that you have to make here when you're determining your vector dot product. So now we've got our gradient vector here, and we determine our unit vector here for both our material and labor points. So all you do is just take your gradient, you take your unit vector here times your gradient vector, and for what they might refer to as a vector dot product. So 213.98 times 0.6402 here for our material, that's going to give us 136.99, and then you add to it your labor amount here, 100 times 0.7682 is going to give you 76.90. Add those two amounts together, those are two of those yellow vectors here, and you're going to come up with your directional derivative or your change in slope here at that specific point here, 5 and 6 at 213.89. Now, if we did the same thing here at that second point, 67 and 75, we would have come up with a directional unit vector of similar amounts here by going through that same routine here to calculate it. And then our gradient vector here, we already calculated that. It was essentially 0 here. So you can see our change here is minus 0.02, or just sitting at 0 here. Our slope is 0 here. So okay, so let's go up and let's look at that. So going back to our 3D plot here, we now know what our directional derivatives are here for the first point here and our second point here. That's those red vectors here, and really that's the tangent plane or the change in slope here at those specified points. So if we go over here, we can look at it here. So remember, here's Q is our output here, or our profit, and then material and labor are showing down here. So you can see the difference here for our directional derivative at this first point here that we looked at, 5 and 6. I'm coming up with about $214 here. For every unit of input for material and labor, we're increasing our output or our profit here by $214. So we're sitting at 5 and 6 units here, so we have a number of units we can move in that direction. But at that specific point, that's what we're adding to our profit here. Now, we move over to our other point here, that point that the 0, we have a 0 slope. So the change in unit output here at this point is 0, because that's that second point here. We come up with our 0 output based on our unit vector and our gradient vector here. So these green mesh surfaces that I'm showing here in both cases over here, those are really our tangent plane or the change in slope. So use the computer to plot them out here so you get kind of a good idea what's going on. Rather than just sitting and looking at numbers and formulas and everything, it gives you an idea what's going on. So as you move up your directional or your gradient plane here, the slope is going to get less, and it's going to level off here. So that's the only point I made by looking at these two different points. You can see here when we have initial inputs for material and labor based on our production function, we have a greater output here. And then you're going to reach, in this case, we reach some plateau amount where we're adding no more material and labor. It's not going to really help us any. Matter of fact, we're going to probably go down and lose money here. So we plateaued it out. So you can see what's going on here. Had I plotted out another points, our plane here would have become less and less steep. We'd have moved from 214, well, we moved from $214 unit output down to 0 here. So at some midpoint, at some other point, we're going to be down to a much lesser slope until we hit our plateau here. Okay, so that is our directional derivative. These yellow, going back over here, these yellow vectors here, those are our gradient vectors. And then we have to take that times the unit vector here for material and labor here. So you determine what your gradient vectors are. Then you have to come up with the unit vector for material and labor. You take a dot product, or you multiply those times each other, and that gives you your directional derivative, or the change in output at that specific point that you're looking at. Okay, and then if we move over here, just another shot at it. I've just plotted it out here. We had that ISO curve here based on that first point, 5 and 6 here, an output of 2,650, or that's our equal product curve, just to let you through. Slicing through our production function where we had that first profit that we looked at points 5 and 6 here. And then if we move down here, just another look at our directional derivative, looking at it from just a different perspective here, took some of our planes out. So we had that first point here. You can see it's moving up at 5 and 6 units. We have 214 units. The change in output, we're adding to our profit at that point. And then as we moved here to that other point here, 67 and 75, we're adding nothing. So we're at our plateau here. So you can see that adding any more material labor or producing any more isn't going to give us any. And just looking here at our curve, so we're slightly going down here. I've got a profile of it here, so we would lose a little money by producing more here. Okay, so that's our directional derivative that we had to come up with here to determine really the change in slope, or the change in unit output, or the slope here at any specified point. Okay, so that'll end our discussion.